Hello physicists. Last time we talked about average acceleration. So we found the average rate of change of the velocity. So we found that the average acceleration is equal to the change in the velocity over the change in time, the time interval. Now, we're going to use the same limiting process that we used to find the for the velocity and see if we can find an expression for the instantaneous acceleration. Okay, because if we know the instantaneous acceleration, we can calculate the acceleration at any time exactly, rather than relying on the average value, which is usually just an approximation. So if we can calculate the instantaneous acceleration, then it will serve to be quite useful. Now, let's see if we can use the same limiting process we use. So let's get our car. We have our car, and at time equals t naught equals t, you are moving at a velocity at a v of t naught equals v of t. Okay, so that is your initial velocity. Now your velocity ends up changing, and it doesn't matter if it increases or decreases because we're using vector notation, so it will automatically be described mathematically. So at tf equals our original time plus some interval, delta time, then the velocity will be v of tf equals v of t plus delta t. We're just substituting our tf, our final time, into the expression. So in what this basically means is that in a short time interval delta t, our velocity has changed by some amount. So let's plug this in and see if we can find the average acceleration. So that's v of t plus delta t, that's our final, minus our initial v of t. All of that over delta t. All of that over delta t. Now what do we do? Well, if delta t is very large, then we're basically calculating an average velocity. But what if delta t is very small? Let's use the same limiting process by taking delta t to be so small as it approaches zero. Because as delta t approaches zero, the change in velocity is almost negligible, and we can find the exact acceleration at that time. We don't need, and the approximation value will be very small. So if we take the limit of the average acceleration, the limit as delta t approaches zero, and again, this notation just means I'm going to take this function and I'm going to see what it approaches as delta t approaches zero. So by taking the limit, we see that this value is essentially just a definition of a derivative. It's just a definition of a derivative, the limit definition of a derivative for a function v. So in summation, the instantaneous acceleration, so we don't put avg anymore because now it's the real acceleration, is defined as the derivative of the velocity with respect to time. So it's the rate at which v changes with respect to t. Now, it's a bit shorter last time, but now that we have explored the concept for instantaneous velocity, we've just reapplied those concepts for acceleration. Now, there is one cool thing, and that's how acceleration and position relate to each other. Now, if you remember, our velocity is dr dt or dx dt. I probably did x in the last one. Okay, r is the vector notation. You usually use r for position. So we're going to just use the vector notation. And if I were to substitute this into here, what do we get? That the acceleration is the derivative of the velocity, and then that's the derivative of position. Again, using the vector notation here. And we get this expression. And for those who are new to calculus, this is known as a second derivative. Okay? The second derivative measures the rate at which a function is changing. Sounds confusing, but really isn't. If I had my car at a position here, my car started right here, the rate at which position changes would just be its velocity. So the position changes at a rate determined by the velocity. But because the velocity now changes due to an acceleration, the rate at which the position changes will also change. So in short, if my velocity is increasing, that the rate at which I cover ground will also increase. So thus, the acceleration is the rate at which the rate of position changes. Okay? So we get that the acceleration is the second derivative of position. And these derivative expressions really emphasize the intimate connection between position, velocity, and acceleration. But when we revisit the connection between these three, we'll notice a stunning conclusion about another way in which these three are related to each other. But we'll get that later. Thanks for watching.